Hi everyone. Simulating stuff is usually challenging if you want to simulate ants in a tree or something that's imaginable and possible, but the universe is not so much imaginable. Mark Vogelsberger will have his talk on simulating the universe on supercomputers. Please give him a warm welcome.
The audio is fine, okay. So yeah, I will speak about the universe and simulating the universe, and this is part of my PhD project I'm doing at the Max Planck Institute in Garching near Munich, working on astrophysics. And I will try to explain you in this talk some of our motivations why we run very large simulations on the universe and what we can get out of it. And at the end I will also talk a bit on numerical techniques we use to simulate these things. So my general overview is something like this. So first of all, I will give you typical length scales of the universe and some objects in the universe that are interested, so you get a feeling of the dimensions we're interested in. The second point is then that I want to motivate our work in more detail. And the third point, I will show you very recent simulations we did and simulations that are still running and are soon finished. And then I will focus a bit on scientific output you can get from these simulations. And in the last point, I will explain some methods we use. So first of all, let's look at the playground we are interested in. So this is the Earth, and the typical length scales we are used to are the length scales on the Earth. So the Earth has a diameter of about 12,000 kilometers. And yeah, this is what we are more or less used to. Then the next scale is the solar system, with the sun in the middle. These are about now 6 billion kilometers, corresponding to 20,000 light seconds or 5.5 light hours. So this is our next neighborhood, so to speak. And then the whole solar system is embedded in a galaxy, the Milky Way, you all know. And this is how it looks on the sky. And this is how it looks schematically. So this is now a scale of 10,000 light years. So when the sun is just one star in this Milky Way, and there are lots of other objects, as you can see. And it's a typical spiral galaxy. You can clearly see the spiral structure here. Then the next scale is the so-called local group. The local group is a collection of larger and smaller galaxies, where also the Andromeda Galaxy is part of. You can see this here, the Andromeda Galaxy. And also the Milky Way and lots of other so-called dwarf galaxies, so these are quite small galaxies. And this is now the scale, this is already 1 million light year. Then the next, this is just an example, the Andromeda as seen from the Earth. Then the next scale is so-called superclusters. So you have to imagine that all galaxies you have in the universe usually cluster together and build clusters. And these clusters again build superclusters. And this is the nearest superclusters, and this is now a scale of 100 million light years. And the next largest scale is then the whole visible universe. This is a scale of 1 billion light years, and in total you have then 3 times 10 to the 22 stars in this whole visible universe. So these are the typical length scales we are used to in astrophysics and we have to deal with. Now, what is the goal of our work, or what we are interested in? Well, the question is quite simple. The question is, in principle, where we are all coming from. This is the key question. So this is a small animation showing the Big Bang. This is, of course, not realistic. It's just an animation made by NASA, I think, showing the Big Bang. So this very hot phase. And then you can see that out of the Big Bang, the galaxy formed, the planets formed, the stars formed, so everything formed. And the question is actually, can we describe with physical theories how everything formed, how the structure in the universe formed? So this is the key question of so-called structure formation theories, what we are interested in. And we run the computer simulations and we use other physical models and things to actually understand how the structures in the universe look like. And you can also see in this movie the expansion of the universe, and here you can see the galaxies, and in all these structures we're actually interested. So at the moment we have a standard model for the evolution of the universe, for the structure formation. And this standard model is shown here. So everything started with a very hot Big Bang here. And then you had some quantum fluctuations. And these quantum fluctuations were, so to speak, blown up in a phase called inflation. This is a phase where the universe expanded by lots of orders of magnitude. And then these quantum fluctuations are, so to speak, the seeds of the structure formation, of the further structure formation. So you have a density field of matter, and you have imprinted in this density field small fluctuation, and out of these fluctuations you form everything that is in the universe. And this shows then the whole evolution, and we think today that the universe has an age about 30.7 billion years. And the interesting thing is what we can do today. We can use satellite missions like this WMAP mission and observe the universe at this time. So due to the finite speed of light, we can look in the past of the universe, and if we do such an observation, then we get this result. So this is now the universe about 30 billion years ago, observed by one of the satellite missions, recent satellite missions. And this is in principle a short moment after God actually created the universe. And you can see this is a temperature map of the microwave radiation. So you can see small temperature fluctuations, and these temperature fluctuations are actually correspond to the density perturbations, and from these density perturbations, the whole universe then evolved and grew. And this is a very hot topic, and in 2006, actually, one Nobel Prize, the subject of the Nobel Prize dealt with this cosmic microwave background. So the question then is, can we actually create a virtual universe from these initial conditions? So we know the initial conditions today very well. And the question is whether we can model the whole thing in a way that we end up with a universe that looks from a statistical point of view like our universe. And the answer is, as we know today, yes, you can do this. So you have to, of course, use a very good physical model to describe the universe. Then you have to write a very clever code and use extremely fast computers. And then you can simulate from this point the whole lifetime of the universe, so 13 giga-years or 13 billion years to what we see today. And this background image is actually the universe at a very early time. And if you then use the computer and let evolve these density fluctuations, so this is now starting from a very early time to the present time, then you can see that these density perturbations we had, that they build these structures. So what you get in the end is very filamentary structure and clusters of matter, and this is called the cosmic web. You see also these voids here that build up, and all is done by gravitation, just because the material just attracts each other, and then it forms these structures. And what I show you here is it's not ordinary matter, what you are used to, it's dark matter. So this is a point I will come a bit later to. So what actually do I mean by dark matter? Well, the problem at the moment is, or what we know about the universe, is that it only consists to 4% of matter we are used to. So matter like the Earth, the stars, or matter we are made of, this only makes in total 4% of the whole energy content of the universe. The largest fraction of the universe is made up of something called dark energy, so 73%. Dark energy was discovered 10 years ago, so it's quite new, and we know today that it makes up the largest fraction. And another large fraction is made up by dark matter. Why is this matter called dark? Well, because it does not interact with electromagnetic waves. So it does not shine, and it does not absorb any light. So we cannot observe it with telescopes or satellites, something like this. And from a theoretical point of view, the dark energy is a quite challenging thing, because if you use very simple arguments from quantum field theory and try to get the correct value of dark energy that we observe in the universe, then you suddenly end up with a value that is 120 orders of magnitude of the correct value that we observe. So currently lots of people are working in this field and develop quite complicated theories to describe this dark energy. For dark matter, the situation is a bit better, because we know that the standard model we have for particle physics is somehow not complete. We know that it needs to be extended, and natural extensions of this standard model actually provide us with a particle that has all the properties that dark matter should have. So dark matter particles, as I said, they only interact by gravitation, and particle physics has some of these particles. And the interesting thing about dark matter is that in the next year, or probably in the next year, in CERN, the LHC, the Large Hadron Collider, will go online, and they are, beside other things, searching for these particles. And also on Earth, we have some detectors to search for dark matter, but currently we haven't yet discovered it. But the point is that it's quite probable that these things will be solved in quite short time, so we are currently living at a very exciting period in science. So in all these simulations I showed, the previous one and also this simulation I will show you, they only simulate the dark matter content of the universe. So they do not actually simulate the stars or something like this, they only simulate the dark matter. And the reason why they only simulate the dark matter, because it's just the largest fraction of matter. So you can, for the large scale structure, you can just ignore the baryons and only simulate the dark matter to look at the structure formation processes. And especially if you search for dark matter on Earth with detectors or something like this, then you have to know how dark matter near the Earth is distributed to get an idea what you are searching for, actually. And this is the reason why lots of simulations do not simulate a large volume of the universe, but focus on an object that has the properties of the Milky Way. So the Milky Way is also surrounded by dark matter, and these simulations then simulate the dark matter halo of these of Milky Way-like objects. And this is a very recent simulation, not done by us, but by a group in the USA. And they used one of NASA's fastest machines to simulate a Milky Way-like object. And here you can see now the dark matter distribution. So this is the density field of the dark matter. And you can see in the inner region you have a very high density, and then you have lots of these so-called subhalos. So this is substructure of dark matter. And what I show you next is a new simulation we are currently running. This is the Aquarius simulation, and it's not yet finished. This is, when it's finished, it's the highest simulation, or highest resolution simulation ever done. It takes about 4 million CPU hours, and the storage you need to store it is about a 50 terabyte output. And this is, again, like the previous slide, the dark matter distribution in such a Milky Way-like structure, and you can now clearly see that you have lots of substructure and a very high density in the center. And as I said, the simulation will be finished at the end of January or something like this. And this simulation actually was done by our institute in collaboration with the Virgo Consortium. So just to show you what the Virgo Consortium is. So these simulations are so large that you actually cannot run them from a single institute. You do not have the money for the CPU hours, and you do not have the manpower actually to analyze all the data. And this is why this group was formed, and they run all these high-resolution simulations. And this is, again, a slide. And if you look how this movie now shows how the final object in the simulation just builds. So you have, again, these small density perturbations in the beginning. And then you can see that due to gravitation, now the structure begins to form. And this started again at a very early time. So there you can see the time scale. And the typical length scale here is also more or less the size of the final Milky Way size halo. So this is now in parsec, so parsec is about 3 light years. And you can see clearly this filamentary-like structure. This is typical for these structure formation processes, that you have this cosmic web. And if you now go a bit further, then you can see that the final object here starts to build. So it builds just by infalling material, and this infalling material gets then tidally disrupted and builds a smooth background, and in the end you have a smooth density background